Hi, this will be the fourth example of making an ice table to figure out equilibrium concentrations. So let's see what this problem has in store for us. They're progressively getting harder. Here we have, actually that's a reaction that we saw a couple examples ago. Let's see how they changed this up. We still have a Kc of 54.3, but now we have the initial concentrations of all three molecules. This is different. We're not starting with zero product. We do have product already initially in the round bottom flask. Therefore, our first step is going to be really important because now it's not apparent which way the reaction is going. Is it going to make more product than what it already has, or is it going to make more reactants than what it already has? We got to figure out Q. So QC, that's the reaction quotient when the concentrations potentially are not at equilibrium. Let's look at the equation. We have the concentration of HI squared divided by the concentration of H2 times the concentration of I2. Can you go ahead and plug in your numbers and figure out what QC is? Okay, what I would do is plug in the numbers. HI 0.0424. Hmm. 69.7. What this tells me is that QC, I'll write it here, QC is greater than KC, meaning that QC is too big and we need to lose some products and make more reactants. We need the numerator smaller to get this number lower to equal that number. The reaction is trying to get to an equilibrium, and equilibrium is defined as this expression as 54.3. Okay, let me just write down our conclusion. We could say that the reaction shifts, to the left. We want to lower the concentration of HI. I should have done this in the previous examples. This will tell me that I need to minus some number from the initial concentration. Is that right? QC is bigger. We got to get rid of some of the product. Okay. Number 2. If you've been following the videos, you've done this 3 times. Why don't you pause the video and construct the ice table? ICE. Give it a go. See what you can fill in these 9 blanks. Okay. The initials. There's a different number for each compound. 0.00623 And I'll give myself a reminder that for this ice table, everything is in molarity. I2 0.00414, and this concentration is literally how much HI you have. Don't worry about the 2 just yet. 0.0424. Okay. The change. What did we say? We said that we're going to decrease in HI. Now, the way I do this is that I find the compounds that have a coefficient of 1, and I will either minus x or plus x. So I know that our goal is to get rid of HI, but I don't want to do that right now. I want to take care of these other coefficients. And because we are making product, because the reaction is shifting left, this would be a plus x, and this would be a plus x. Again, that coefficient is implied. It's plus 1x. Therefore, you know what this is? We're losing product as we make more reactant. And for every molecule of I2 we make, we lose 2 molecules of HI. You have to, right? Because it has to balance. Another way you could think of it is you can minus x, but you lose 2 of them. So I had it in a different format in a previous example, but you could also write like this. It's minus x, but it's twice minus x. Hopefully you understand how to do that, and maybe understand my little trick. I'm literally bringing down the coefficient. Equilibrium. Oh boy. I'm already sweating because every equilibrium concentration looks to be different. And this is also minus 2x. Okay, I am okay with this. The ice table, I think, is set up properly. I'm not enthusiastic that we're going to have to solve for x, though. But anyway, let's give the equilibrium expression. Kc equals, it's just this one up here, right? Qc meaning that it possibly is off equilibrium, but Kc is at equilibrium, the HI concentration squared divided by the H2 concentration divided by the I2 concentration will equal 54.3. That was given. Plug in these numbers. Okay. HI 0.0424 minus 2x, man, squared already. Well, we predicted this. This is not going to be easy, super easy. H2 0.00623 plus x times 0.00414 plus x, and in previous examples, I think example 2 and 3, we were able to take the square root of each term, numerator, denominator, and the equilibrium constant. We can't do that here. This denominator is not squared. Okay, so that's a little bit unfortunate. We are going to have to, I call it expand, or do your multiplying the in and the outs. I forgot the mnemonic for that, but here we go. 54.3. I don't know any shortcut to do this by hand. I'm just going to go ahead and let's do the numerator first. So it's this squared, 0.0424 squared. Okay, so that's a term that doesn't have the x. 0.001798 minus. So what's happening here? Minus 2x is multiplied by that number, and then the same thing for the outer. Okay, 0.0424 times 2x. So that's and it's negative, so it's negative 0.848. But we have we do it again because it's squared. Does everyone understand? I'm not making myself very clear. So let me expand this. 0.0424 minus 2x times 0.0424 minus 2x. So I did this part already, and then I'm going to do the outer part. It's the same number, so we're just going to multiply this by 2. Okay, so the x term is negative 0.1696x, and then, oh boy, and then we multiply these two, and that's a negative times a negative, so that's positive 4x. This is my x squared term. Okay, let's try this one. I'll do the easy one first. 0.00623 times 0.00414. As you can tell, I haven't taken algebra in decades. Oh my goodness. We're going to use scientific notation. 2.5792 times 10 to the minus 1, 2, 3, 4, 5. Okay, and now the x is, okay, this is a little bit easier. 0.00623 x plus 0.00414 x. This is plus 0.01037 x. Then finally we have x squared. Okay. When we cross multiply, so I'm not going to do this, I'm not going to show you the work, but what I'm doing next is I'm cross multiplying the denominator by this number, and then I'm bringing everything to the left side because we're going to have to use what's called the quadratic equation. So if you do that, we actually get 50.3x squared plus 0.735x minus, is it really going to be minus? Let's double check the last term. So I take this number, 2.5792 times 10 to the minus 5 times this number, 54.3, and then subtract this number, minus 0.001798. Okay, and that's what I got. It's a negative. Oh man. That's it. So it's negative, we'll just call this, we'll call it 3.975 times 10 to the minus 4. And then, since everything is on the left side, this equals 0. This is going to be using the quadratic equation. This is ax squared plus bx plus c equals 0. This is a way to solve for x. And the quadratic equation is, I'll write off to the side, x equals negative b plus or minus the square root of b squared minus 4ac divided by 2a. There are quadratic solvers on the internet. Those of you who are in algebra most likely are using a graphing calculator that has that you could program the quadratic equation. There's this plus minus business, so that you are going to get two answers. And again, so I would honestly, you should be able to do this by hand, but it's going to take forever if I try to do it. In the quadratic solver, it spits out two numbers. X equals 5.25 times 10 to the minus 4, and the ice table is in molarity. And there are two valid answers using the quadratic equation, and negative 0.0151 molar. So I think in every case when you have to use a quadratic equation and get these two answers, only one of them will make sense. Because let's take a look at our equilibrium expression, equilibrium concentration. It does make sense that if we take this number plus x, okay, we get a positive concentration. And this one plus x, positive. This one, well, we multiply this by 2. Yeah, this will be positive as well. But look what happens if we use this number. Let's plug it into the H2 concentration. 0.00623 plus x, but x here is negative, so minus 0.0151. So it's a negative. We can't have a negative concentration. We can't have a negative concentration, so we are going to get rid of this. Your x that you're using is this, and you just need to plug it in each of these to figure out the equilibrium concentration. Let us do that. And see what numbers we get. They're tiny, but I think we'll be able to see a difference. 0.00623 equals minus x, 5.25 times 10 to the minus 4. Okay, yeah, I'm good with that. So, is that right? Yeah, that's right. So for the concentration of H2, we get 0.00571 molar. So there is a change. Okay, it's small, but you do see a difference from where it initially started to what it ended up with. And it did I do this right? I didn't do this right. Because the number should be bigger. This number should be bigger. I accidentally put minus. Okay, let me try this again. My bad. I'm doing this equation here. 0.00623 plus x, 5.25. Let me do parentheses. 5.25 times 10 to the minus 4. That's good, we double checked. Does it make sense? Okay, now that makes sense. You can see that number is bigger than the initial amount. 0.00676 molar. Okay, let's do iodine. 0.00414 plus x again down here, plus 5.25 times 10 to the minus 4, and that is our iodine concentration, equals 0.00467 molar. Okay, now let's see what HI is. Understanding that our equilibrium constant is positive. It's always going to be positive. It's greater than 1. Let's see if this makes sense. 0.424. 0.0424 minus, in parentheses, let me give another parentheses, 2 times x. 5.25 times 10 to the minus 4, close those parentheses. Alright, does that make sense? We are lower than what we started, but that's what we predicted. We're consuming some of the product because we have the reaction going to the left. Equals 0.04135 molar. Oh, you don't see that? Okay, that was difficult and time consuming because we had to go ahead and expand the denominator and the numerator, and then use the quadratic equation to solve for x, figure out which x makes sense, and then plug in x into our equilibrium row to figure out our equilibrium concentrations. Example 5 is going to be interesting because, well, we're going to again use or potentially use a quadratic equation, but I'm going to show you an approximation that will make life much simpler to solve for x. But don't think you could use that approximation for every instance. We did this properly. We had to use the quadratic in this case. We have to use the quadratic in this case. Okay. I will tell you the conditions where you don't have to use the quadratic, even though you have an expression that gives you that will give you an equation in the quadratic form. I totally butchered that. Just wait for example 5.